there was a field that a farmer had that was growing onions, and it was a 20-acre field, but it had been two fields that were from historically two different 10-acre fields, but they combined it and made one field to grow these onions. And when they did the sample for the whole field, the pH was 7.2. And so the guy thought, oh, onions grow great at that pH, so he planted it. Well, half the 10 acres of the field died, and the other half did just fine. Well, they went back and sampled the 10 acres, and the pH was like 5.4 on this side, and it was 8.2 over here. So when it averaged, it was 7.2. So, okay. So sometimes the more testing you do, you can avert disasters down the road. So.
I'm Brady Stover. My passion is agriculture, agronomy, and sharing my experiences. Join me on my journey through the Pacific Northwest. So after taking our soil sample in last week's video, we are here at the soil lab to turn in the soil sample to get an analysis, and we are here in Moses Lake at Test Analytical Services. Hi. So here we're at Best Test in Moses Lake, Washington, and this is the owner and operator, Steve Jones, and he's going to walk us through bringing in our soil analysis and what all is entailed in the process.
Then, ever since I was just 11 years old, we moved up from Idaho up. My dad moved up here to Washington, and then so I've been here pretty much my whole life. We started Best Test in '93, and so next year will be 30 years. And then I worked across town at another soils lab for 9 years. So 2 more years, I'll have 40 years of doing this. So the first stage begins right here. These samples just arrived in the mail, so they're getting them organized, and they'll log the samples in, and we'll give each soil sample a sample number, and so we can track it through the process. And then after they're done here, then we go clear to the very back of the building. So take you on back there. Okay, well, this is the lab here, and then we continue through the lab to the drying room. And this is where they prepare the samples to be tested.
So the bag comes back here?
Yeah.
And then it comes into the drying room here?
Yes.
Okay.
Yeah. And then I think those are probably about some of the first samples that came in today.
Okay.
And then they'll put them on trays and then put the samples in these drying ovens.
Okay.
And we've got several drying ovens for this time of year when we're real busy. And like these samples that came from the Palouse, and so the dryland farmers are interested in the moisture in the soil, and so then we'll take a sample of that soil and put it on these little aluminum pans, and then they'll get put into an oven to dry at a little hotter temperature than what these ovens are set at. So, and then once the samples are dried, then later this evening or later afternoon, depending on how long it takes to get the samples dry, and like I say, right now, if like these Palouse soils, they're a little wetter, and so we do crank the heat up a little, so it'll heat them up faster, so we can get them dry in about 4 hours, 4 or 5 hours.
Okay.
And then we'll come over here and then set up the grinding process. There's a fan for taking the dust out, and then there's some flails inside here that when you turn it on, these stainless steel flails break up the clods, and then there's this has a a bottom that opens up after the soils are ground, and then it drops it onto this little pan with a 2 millimeter screen on it, and so then the soil will fall down onto the screen, and then we'll sift it through the screen and then put the bag on the end and then dump the soil into the bag. And then the particles that are, the sticks and the rocks that are bigger than the 2 millimeter then just go into a waste bucket. And then after the soils are dried and ground, they come in here, and then we start weighing the samples out. At the evening before, we'll print out the lab slips so we know what tests need to be run on each soil. Usually there's multiple tests that they want run on each soil, and so they're using those lab slips to weigh out trays, a certain amount of soil for a given extraction. And then once they're weighed out, then Janet's over here putting the extracting solution into the trays, where the solution then will extract out the elements that we're concerned about, and then she's putting them on a shaker over here for a given period of time, depending on the extraction. And then after they're extracted, they'll be filtered into these other trays, so that we're getting the elements that we want off of the soil into solution, and then we'll test the solution after they've filtered. Down below here are the different extracting solutions. And for instance, this one is a potassium chloride solution, and we're extracting for ammonia, and actually ammonia and nitrate, calcium, magnesium, sodium, also aluminum, manganese, and iron. So all those are coming off of that extraction.
How much soil per sample do you need? So are you using the whole bag that gets brought in?
No, actually, like she's doing the pH test, I think using 20 grams to do that one. The Olson test is a 20-to-1 extraction, and so we use 2 grams and add 40 milliliters of solution. Most of the tests are 5 grams and 25 milliliters. It's a 1-to-5 ratio, and some of them are a 10 ratio. And then the DTPA is a 1-to-2 ratio, so we'll weigh out 12.5 grams for 25 milliliters of extracting solution.
Okay. We offer a lot of different options for different soil tests.
Right.
What do you believe should be the minimum for each crop? I mean, more intensive for a potato or an onion compared to a winter wheat.
Right.
What are your suggestions?
Yeah, it's how well do you know the soil? If you're renting ground and it's your first time with that field, you should do the whole thing. Okay. Yeah, Gracie is doing the pH soluble salts tests here. She does the after they're mixed and they've settled for a little while, then she'll measure the conductivity of the soil, and it's a one. What we're doing is 1 part soil, like 20 grams of soil, 20 grams or 20 milliliters of water, and then mixing it. And they're on the shaker first, and then she kind of just makes sure they're well mixed. and then she reads the conductivity, and then after she reads the conductivity, then she'll go back and read the 1-to-1 pH, and then after the 1-to-1 pH is read, the ones that are below 6.5 pH, she adds a buffer solution. For like wheat, once you start getting below 5.4 pH, then your yields start going down. For alfalfa, if it's less than 6.5 pH, your yields will start dropping. And so you need to know how much lime to add to the soil to neutralize that soil acidity and bring it back up to where the crop can be most productive. And right now, I know, like for the dryland wheat farmers, it's been tough because that with the no-till, they've created these zones where they have a lot of acidity down in the 4 to 6 inch range, and that's right where you're planting that seed, and it struggles trying to get going because the pH is so low. So, like over here, Daniel's making a dilution, taking an aliquot out of these filtered trays, and then making a dilution, and then he'll go to an instrument to test for the potassium is what he's setting up there. And then right over here, they've taken another aliquot and put on this tray, and it's testing for the phosphorus. So different reagents are going through these instruments, and then once the color's developed, it goes through a detector to determine the amount of color, and then you run some reference standards to make a standard curve, and then the concentrations are taken off of that. Yeah, it's great that they have instruments like this to do all this work.
Yeah. How much time does that save
So
you?
it saves a lot of time. It saves. We used to do this all on a little spectrometer, and by hand, one sample at a time. Now she's getting ready to do this. We still use the old spectrometer to do the organic matter, but that won't be done till later this afternoon. Okay. But it's a colorimetric method, and so we got a little vacuum pump, and then we can, with my finger on here, it creates a vacuum. Suction. Yeah, and then I can suck it out. And we can fill it back up, and there we go. And anyway, then the light beam goes through there, and it can detect the color, and then from the color we can determine the concentration
Of the organic matter.
Of the organic matter.
Okay.
Yeah. Okay. So in this room is where a lot of the analysis occurring with an instrument called an ICP, inductively coupled plasma. It's an instrument where we take the sample and it's pumped, made into a mist, and that mist goes up into a flame, and this flame in here is about 10,000 degrees centigrade. It's a plasma, and the electrons in that plasma pick up that energy, and they go from their stationary orbitals around the nucleus of the atom, and they'll pick up energy and go to a higher energy orbital. And then as it moves up a little further, it'll cool down, and then that electron will want to go back to its steady state orbital. And when it does that, it releases a wavelength of light to get rid of that energy. And there's lots of different electrons, a lot of different orbitals, and so there's lots of different energy levels, and they all release different wavelengths of light when they go back to their standard orbital. But somebody figured out that there's a few electrons that are jumps that goes from one orbital to another orbital that is unique to that atom and no other atom. And so then by tuning an instrument to detect that wavelength of light, you can determine the presence of that atom in solution, and by how bright the light is, the concentration of that atom in the solution. So there's a camera. This light is picked up and goes through a prism to separate the wavelengths, and it goes onto a camera, and each pixel of that camera represents a different wavelength of light. And so the computer just looks at that pixel and says, oh, okay, well, that's a calcium pixel wavelength, and here's the concentration. And so by running standards through there, we can run a standard curve, and then from that we can determine what the concentration is in that solution. Go over here, and this is a list of the things that it's tested. And then up here are the different wavelengths that it's testing.
Okay. So we see sodium and magnesium,
yes,
calcium,
and
manganese.
And there's some wavelengths. A lot of these elements, there's multiple wavelengths that are unique to that element, and so you run several of those wavelengths, and that way you can look at it. Or if one fails, because maybe there's a small amount of sodium that interferes or something, and then you got a sample with a lot of sodium in it, then it'll might mess up one of those wavelengths, but you have the other ones to compare to.
Okay.
And so that's why we run. And as you can see here, they all came about the same on the magnesium here, 2.3, 2.3, 2.3. And the calcium, 8.2 and 8.1, so there's a little bit of difference, but
so then you can get a consistent average. And
yeah,
if there's an outlier, then you'll know you
can throw that one out, or
okay,
if it didn't read properly. So anyway, that's pretty much the different processes that we're running to generate the lab numbers, and then all that goes into the computer. You work through the data, and then dump that data into our computer program to generate the soil reports. Okay, oh, you're working on the new program. Oh, okay. So here's Daniel. He's setting up to read the potassiums. This is the old way, this is an atomic absorption spectrophotometer where it's just doing the one element at a time.
Okay.
So that's in a short period. Soon we're going to be able to do this test on another ICAP. This is a combustion analyzer for nitrogen and carbon here. So a LECO analyzer, and that's what for plant tissue. And you can run soil total carbon, total nitrogen on soils, but mostly we use that for plant tissue testing.
Okay. But you can see how much carbon you have in the soil.
Yeah, which isn't very much.
Yeah.
So we have different formats, for different customers. This is the WSU does wheat variety trials, and so they want to know what the nutrient status. So they have a way to compare one site to another site on the yields that they have. Okay, so here's one where the sodium's 10% of the exchange site. And that's kind of probably the upper limit for around here where you'll start seeing negative effects. When somewhere in that 7 to 10% range is when you'll start seeing negative effects due to the sodium. So, and the other problem we have nowadays is everybody bans their fertilizer. So maybe right where the band was, you might have 50 parts per million phosphorus, but a foot over, it might be 8 parts per million phosphorus. So now how do you deal with that variability? So there's a lot of issues with soil testing, and I don't know if we know all the answers yet.
Right.
So.
Yes. So
we do appreciate, Washington State, Oregon State, and University of Idaho, and what they do, because we're dependent on a lot of these graduate students developing these relationships, and so it's that's kind of a slow process, and we need to keep that end going too, so we can provide realistic fertilizer recommendations and things.
Well, thank you for your time.
You bet. Thank
Appreciate
you.
it.
Thanks for coming by. Yeah.